Today we're going to finish section 1.2, exploration with patterns. We had looked last time at two different kinds, specifically, like in depth, at two different kinds of sequences. Do you remember what kind they were? Arithmetic and geometric, and we had looked sort of on the surface level at a couple of others too. But those two ones were the ones that we dealt with mostly last time. And we ended talking about the fact that sometimes things are not arithmetic or geometric, but they sort of have another pattern involved. This is the example I'm thinking of. I did this where I said, okay, let's look if we subtract these again. Notice that the first differences were not arithmetic, but the second differences were, so that's where we left off. All right, so we're going to start today with a problem where we find a counterexample. This problem says that we're going to look for a counterexample. So if you'll remember from last time, counterexample means something that's proving it's not true. Okay? Find a counterexample to show, basically, that this equality is not true. That's what you're looking for. You're looking for a number that when you plug it into both sides, it's not going to work. So can somebody give me an example of a number n that makes this not work? Don't think too hard. 10. Okay, so if we do 10, let's check it out. So if we have 10 plus 5, and do we divide by 5? What's 10 plus 5? 15, and 15 divided by 5 is 3. Okay, so we get 3 on the left-hand side, and on the right-hand side we have 5 plus 1, which gives me 6, right? And these are clearly not equal. There's actually a lot of examples that you could use on this one. There are counterexamples to making something work. Sometimes that's not the case. Sometimes when you look for a counterexample, you try a whole bunch of things before you find one that works. And maybe you even can't find one that works, even though you know there should be one that works, kind of thing. You know, it becomes more difficult. This one's an example of one where it's not too hard to find one that works. What is a number that you see that would actually make it work? Is there anything that you can see off the top of your head that would make it work? 0 would actually make it work. So if you happen to try 0 on this one and you were like, oh, it works, then you're not done. You would have to keep looking. Why do you think a student might actually tell you this if they were doing a problem? Because this is not that far off from the kinds of errors that I have students make at the college level. What might they be thinking if they made this error? Nobody knows?
N plus 5 divided by 5.
Okay, so what would they be making the error thinking they were doing? How would they have thought through the problem?
It's 5 over 5 is 1.
Mm-hmm.
So they might be like, let's look out first and then how do you...
Yeah, and I actually, even at the college level, have students who will do that. They'll say, oh, look, I can reduce the 5s. But they forget that also the n would have to be reduced to do that, right? And so there's this idea that I can cancel these out. 5 divided by 5 is 1, and so that leaves me with the n, and then plus 1. So that's what this question at the bottom is asking. It says, what reason might you speculate for a student making this conjecture? So write down some variation of what you're seeing that happening with the red on my screen. What is the student doing? How are they thinking through this problem? If they're conjecturing that n plus 5 over 5 is equal to n plus 1. We're going to shift gears on our next set of questions, problems, and whatnot. We're going to talk about something called figure it numbers. So just a show of hands, how many of you would say that you learn visually? That's me. I learn visually. So I'm one of those. So we're at about maybe 60% of the class. I have a daughter who learns auditory. She can memorize anything if she listens to it. And I don't mean like just I said it, now she memorized it, but she has like a music CD with memory verses on it for a Bible program that she does at our church. And she's memorized tons and tons of verses, but she does it by listening. So we're going to take a look at something that's really good for a visual learner today, and these are called figure-it numbers. They're based on visually geometric patterns. These examples are not arithmetic or geometric. Such numbers can be represented by dots arranged in the shape of certain geometric figures. This is one of those highly unhelpful sort of things because I've used geometric 3 times in here and I've meant 2 different things by it. Okay, so if you want to replace the geometry at the beginning and the geometry at the end just with the word picture or diagram, we could go with that. I'm going to show you triangular numbers first. And so if you have like a marker or something that's got just a broader tip, it might be helpful for drawing these. If not, it's not a big deal. But figure-it numbers will look like this. So here's my first one. So this is the first value in the pattern, the second, the third, and the fourth. So do you see what I mean by visual and by geometry? It looks like the shape of a triangle. That's why the name is triangular numbers. What I'd like for you to do after you've drawn the 4 that I drew is to draw the next one. What would the next one look like? After you've drawn it, find a partner nearby and just check and make sure that your pictures look, roughly speaking, the same. Okay, so visually speaking, what is the pattern you see here? How did you develop the next number or diagram in the sequence?
You added another dot at the bottom one.
Okay, so you even thought about it in a different way than I did, but that works. So your idea was we could take what we have here, add an extra dot to the end, and then fill these in all the way up till we have a triangle. Did anybody think of it differently? Yes?
You just add another row on the bottom, that's the next number.
Yeah, you could think of it that way too. That's how I think about it. You could add an additional row to the bottom of the diagram you already have. That's just one more dot than the previous row had that was on the bottom. All right, cool. So what we're going to do next is we're going to count the dots and we're going to write out the numerical pattern that's associated with these triangular pictures. So your first number would be 1, right? The second one would be 3. What comes next? 6? 10, And then what about in the picture that you drew for your 5th number? How many were in that one? 15. Now I want us to take a look at these numbers for a moment because they actually are something we've seen before. Okay, that didn't do what I wanted it to do. Let me try that again. Okay, so we're going to look at that pattern that you just created, 1, 3, 5, I'm sorry, 6, my bad, 6, 10, 15. And I'd like for you to find the first differences. Now, if you remember from last time, first differences means asking yourself, what do I have to add to get to the next value? So on this first one, it would be 2. And then what? 3, and then 5. And if you think about the pattern kind of in the way that, is it Haley? That Haley said, you can kind of see where the 2, 3, 4, and 5 are coming from, right? By adding an additional row on the bottom that's just got one more than the row before, kind of lends itself to that description. But you'll notice this is not arithmetic, right? What would this look like if it were arithmetic? What would happen here?
The same number.
Be the same number every time. But what would happen if we did this process one more time and we found the second differences? What do we get? 1 every time. And I heard somebody say it's the same number. So here the second differences match. What if they didn't match at that step? Could we do it a third time? We could. We could do it again and see what happens on the third iteration of this, the third differences and so forth. Let's take a look at another type of geometric, or figurate numbers, excuse me. These are called square numbers. Let's have some more space. All right, the more dots I got, the more sloppy my diagram looks. Sorry about that. It's easier to be off-center, like on the triangles, than to be actually in rows like this one. So first thing I want you to do, after you draw the 4 figures I've drawn, I want you to draw the 5th figure. And after you've drawn your 5th figure, compare with the neighbor again. Okay, so if you're describing this pattern to me, just in words, what might you say? What's going on with this pattern?
I just saw this like adding 5 to the bottom and then 5 on the side.
Okay, so you added a row to the bottom that's one bigger than the row before and just filled in the other row. Does that sound good? Did anybody think of it any differently? Okay, that's fine. Let's write out our numbers that go along with this pattern, right? So the first number is 1. The second one would be 4. What's the next one? 9. And then the one you drew was 25. Very nice. Okay, so looking at the numerical pattern here, we're going to do the same thing we tried to do last time. In fact, before we do that, I want you to kind of notice, normally, it's not so easy to sort of figure out what the equation is for a pattern. This one's actually pretty easy. Does anybody notice when you write the numbers down what this equation is for this pattern? It's n squared. These are all square numbers, which makes sense because it's a square, figuratively it's a square number, right? So this is n squared. So like the next one would be 36, and then the next one would be 49 and so forth. They're all square numbers. So I wanted to draw your attention to that because sometimes that will happen. All right, so let's find the differences and see what happens. The first one would be 3, and then what? 5. Okay, so they do not have a common first difference. But what happens if you do it again? There are 2's everywhere. So this one also has a common second difference. All right, so on both of those examples, we did a type of reasoning. We talked about the 2 types of reasoning last time, inductive and deductive. Do you remember the difference? Do you remember which one these are? What type of reasoning are we doing on these 2 examples when I said find the next one in the pattern? It's the other one. Inductive. Let's go back to our definitions just to make sure everybody's on the same page because they're going to ask you some of these in your questions in your homework. Inductive reasoning is making a generalization You know, a prediction is another way of describing that. A prediction based upon patterns, and that's what we were doing. We were predicting or generalizing what was happening next based on the patterns that had already happened. So these are inductive reasoning. Now, we're going to talk a little bit about an actual scenario that happened. This happened a while ago now. In 2011, they did some restructuring at the university, and they created the College of Science and Math. Before, we had both, the science and math had been underneath arts and sciences, and it was all grouped together, and then just kind of split it apart. So we had a meeting at the beginning of the year, and on the board, the dean, which was Dr. Blue at the time, had written the number 3.1415 ... and asked us to find the next two terms in the sequence of numbers. Without talking with anyone, what would you say is the next two terms in the sequence? So write down what you believe the next two terms would be and explain why you think so. Okay, somebody offers a suggestion. What did you write down? 1/6. So show of hands, how many people wrote down 1/6? Okay, did anybody write anything else down different than that? What did you write down? 1/9. Okay. So somebody who put it down a 1/6, tell me why you put down 1/6. Was there anything else besides 1/6 or 1/9? Okay, I'm going to put down what I wrote. I wrote down 9/2. Who wrote down 1/6 that wants to share why you think it's 1/6? It looks like a pattern. Okay, so after the decimal point, you had 1/4, 1/5, and so you're kind of thinking about these numbers as being like 14, 15, and the next one seeming to be 1/6 seems reasonable. What did you think about with your 1/9?
Memorize their own numbers of pi.
Okay.
That's what I thought it was then.
But that's what the 9/2 is.
Yeah.
So you were thinking like I was thinking as well. Okay, so we'll just mark this one out. 9/2 is another possibility. If you do 3.1415, the next two digits of pi are 9/2. And so that was actually, so we're in a room of science and math people, and you guys all looked at it and you said 1/6, duh. I mean, pretty much, right? And you're like, I don't even know why she's asking this question. What a stupid thing to ask me. All of us sitting in that room were going, 9/2, duh, what a stupid question. Why are you asking me? Because we thought about it in a specific way that was specific. It was to our field, right? To what we do as a part of our everyday lives, or at least somewhat. And you thought about it because, in the way that you did, in part at least, because I just gave you a whole bunch of examples that looked a lot like that, didn't I? So what does that tell you about inductive reasoning? Because that's what you just did again. You did inductive reasoning. So did I. I came up with 9/2. You came up with 1/6.
It's based on perspective.
There's perspective involved. So I think I like the way you said that. I'm going to write that down exactly. It's based on perspective. In particular, there may be, now there always, it isn't always true, right? But there may be more than one, how do I say it, legitimate generalization. Okay, pretend like you can see the word generalization at the end there. I ran out of room. Okay. There may be more than one legitimate generalization. Part of it's based on perspective. Part of it would be based on what you're using to just make that conjecture, not necessarily even perspective, but background or history or things like that too. So just be aware that sometimes there's more than one right answer. Okay? All right. That's it for 1, 2.